Tonight, we begin a slow journey upward, away from the ground beneath our feet and into the vast invisible ocean that surrounds our world. The sky. It stretches endlessly above us, familiar yet mysterious, calm one moment and violent the next. We live our entire lives at the bottom of this ocean of air, breathing it without thought, watching it change colors at dawn and dusk, listening to it whisper through trees or roar in storms. Yet most of what happens above our heads remains unseen, unnoticed, and deeply misunderstood. Weather is often treated as background noise to human life, a forecast glanced at, a complaint made, a storm endured. But weather is not merely an inconvenience or a convenience. It is a living system, endlessly moving, endlessly interacting, shaping landscapes, ecosystems, and civilizations. Weather is the planet breathing. The air around us is not empty. It is dense with motion. Molecules collide billions of times each second. Heat rises, cold sinks. Invisible rivers of energy flow from equator to pole, driven by sunlight and the slow rotation of Earth itself. The atmosphere is never still. Even on the quietest night, currents shift above us, clouds drift unseen in darkness, and pressure waves ripple across continents. From space, Earth appears wrapped in a thin blue veil, fragile, delicate, almost impossibly small compared to the vastness beyond. That thin veil is all that separates life from the vacuum of space. Within it exists every breath ever taken, every storm ever born, every cloud that has ever crossed the sky. And it is within this fragile layer that weather comes alive. A single cloud drifting across a summer sky may look soft, harmless, almost weightless. It appears as nothing more than a smear of white against blue. But the reality hidden inside that cloud is staggering. A typical cumulus cloud can contain hundreds of thousands of tons of water. In fact, some storm clouds weigh more than 1 million elephants combined. How can something so heavy float? The answer lies in scale. The water inside a cloud is not collected in drops large enough to fall. Instead, it is divided into countless microscopic droplets, each so small that air resistance easily holds it aloft. Rising warm air continually lifts these droplets, suspending entire lakes in the sky. It is one of nature's great paradoxes, immense weight disguised as lightness. When you look up at a cloud drifting lazily overhead, you are looking at gravity temporarily defeated. But clouds do not always remain gentle. As warm air continues to rise, clouds can grow taller, darker, and more powerful. Inside them, droplets collide, merge, and grow. Ice crystals form, electrical charges separate. What began as a peaceful structure becomes an engine of violence and energy. Lightning is born. In a fraction of a second, electrical tension built up over miles of sky releases itself in a jagged flash. The bolt heats the surrounding air to temperatures hotter than the surface of the sun, more than 30,000 degrees Celsius. For an instant, the air becomes plasma, expanding violently. That explosive expansion sends shockwaves racing outward, shaking the sky itself. We hear those shockwaves as thunder. Thunder is not a sound produced by clouds colliding or gods shouting from above. It is the sound of air exploding under sudden heat. Depending on distance and terrain, it may crack sharply overhead or roll slowly, like distant drums across the horizon. Each rumble tells a story of immense energy released in the blink of an eye. Lightning is both destructive and life-giving. Its energy helps fix nitrogen in the soil, nourishing plants and sustaining ecosystems. Even in its violence, it participates in the cycle of life. Rain follows. Contrary to the way it is often drawn, raindrops are not shaped like teardrops. The smallest raindrops are nearly perfect spheres, held together by surface tension. As they grow larger, air resistance flattens their underside, giving them a shape closer to a rounded bun than a falling tear. If they grow too large, gravity wins, and they break apart mid-air into smaller droplets, scattering water across the sky. Each raindrop falls on its own journey, shaped by gravity, wind, and invisible currents. Billions of these journeys happen every second during a storm, quietly replenishing rivers, nourishing forests, and reshaping the land grain by grain. When rain strikes dry earth, something ancient is released into the air. The familiar smell that rises after rainfall has a name: petrichor. It is created by oils released from plants during dry periods, combined with geosmin, a compound produced by soil-dwelling microbes. Lightning adds ozone to the mix, sharpening the scent. When you breathe in that smell, you inhale a chemical memory of soil, plants, microbes, and sky, a reminder that weather connects every layer of the living world. Snow tells a different story. Snowflakes form high in cold clouds, where water vapor crystallizes directly into ice. Each flake grows according to temperature and humidity, forming intricate patterns of symmetry. Some fall slowly, drifting as if reluctant to land. Others tumble faster, depending on size and structure. Under rare conditions, snowflakes can clump together into massive clusters, wider than coins, sometimes even larger than dinner plates. No two snowflakes follow the same path. Blizzards arise when wind and snow merge into something far more dangerous than snowfall alone. Visibility collapses, direction disappears, sound behaves strangely in the swirling white. Temperatures plunge, and exposed skin can freeze in minutes. To be caught in a blizzard is to lose the horizon itself, to exist inside a moving wall of cold. And yet, even blizzards have beauty. They erase the world, covering it in silence and white, transforming familiar landscapes into blank canvases. Hail forms in towering storm clouds where powerful updrafts repeatedly lift water droplets into freezing air. Each time the droplet rises, it freezes another layer of ice. Over time, hailstones grow ring by ring, like onions or tree trunks recording their history. Some grow large enough to shatter windows, flatten crops, and dent metal. A few have grown larger than volleyballs, falling from the sky as frozen monuments to chaos. Tornadoes take this chaos even further. A tornado is not merely strong wind, it is rotation concentrated into a narrow column capable of extraordinary violence. Winds can exceed 300 miles per hour. Objects become weapons. Straw can pierce wood. Cars can be lifted and thrown. Entire buildings can vanish from their foundations. Despite their power, tornadoes are fleeting. Most last only minutes. They appear suddenly, reshape the land and disappear, leaving behind silence and destruction. Hurricanes, by contrast, are slow giants. Born over warm oceans, they feed on heat and moisture, growing into massive rotating systems hundreds of miles wide. A mature hurricane releases more energy in a single day than all of humanity's power plants combined. Most of this energy is released as heat through rainfall, while the rest emerges as ferocious winds and towering waves. At the center lies the eye, an eerie calm surrounded by violence. Winds fall silent, clouds part. Sometimes the sun appears, but this calm is temporary. Beyond it, the eye wall rages with the storm's most powerful winds. Monsoons shift the rhythm of entire continents. Seasonal changes in wind direction bring months of rain to some regions and drought to others. Rivers swell, fields flood, forests awaken. For hundreds of millions of people, life depends on the timing and strength of monsoon rains. Cultures, festivals, and agricultural cycles are woven around their arrival. In stark contrast stands the Atacama Desert, one of the driest places on Earth. Some regions there have gone decades without measurable rainfall. The soil is so barren that scientists study it as an analogue for Mars. And yet even here, life persists. Fog delivers moisture, microbes survive, and on rare occasions when rain falls, the desert explodes into color. Weather does not distribute itself evenly. Some places drown in rain, others starve for it, some burn, others freeze. Heat waves arrive quietly, without thunder or spectacle. Air grows still, temperatures climb day after day. The human body struggles to cool itself. Cities trap heat, creating islands of warmth that offer no relief at night. Heat waves kill more people globally than storms, floods, or earthquakes, silently, relentlessly. Fog lowers clouds to the ground, erasing distance. Sound dulls, movement slows, roads vanish. Despite its softness, fog can be deadly, grounding planes and causing collisions. And yet to walk through thick fog can feel dreamlike, as though reality itself has softened. Every form of weather tells a story of balance between heat and cold, pressure and motion, chaos and order. Above it all, the atmosphere continues its endless movement, driven by sunlight, shaped by Earth's rotation, and tied to oceans, land, and life itself. This is only the beginning. Because the weather does not stop at storms and rain, it reaches into space, it shapes history, it whispers through ancient ice and future skies. As we rise higher into the atmosphere, it becomes clear that weather is not born from the sky alone. Beneath the clouds, beneath the winds, lies another restless world, the oceans. Covering more than 70% of Earth's surface, the oceans are not passive bodies of water. They are vast reservoirs of heat, motion, and memory. They absorb sunlight, store energy, and release it slowly back into the atmosphere. Without the oceans, Earth's weather would be violent, erratic, and largely uninhabitable. The atmosphere and the ocean are partners in a continuous exchange. Heat moves between them. Moisture evaporates from the sea and returns as rain. Winds push across the surface, stirring currents that stretch for thousands of miles. Together, they form a single planetary system, one breathing, circulating engine. Ocean currents act like enormous rivers flowing through the sea. Unlike rivers on land, they are driven not by gravity alone, but by differences in temperature, salinity, and the rotation of the Earth. Warm water is lighter and rises. Cold water is heavier and sinks. As these differences play out across the globe, immense currents are born. One of the most influential of these currents is the Gulf Stream. It begins in the warm waters of the Gulf of Mexico, carrying heat northward along the eastern coast of North America before crossing the Atlantic toward Europe. As it travels, it releases warmth into the air above it. That warmth is carried inland by winds, softening winters across much of Europe. Cities at the same latitude as frozen regions of Canada enjoy comparatively mild climates because of this invisible river of heat. Without it, much of Europe would resemble Siberia, colder, harsher, and far less hospitable. The Gulf Stream is not alone. Around the planet, similar currents form a global conveyor belt, transporting heat from the equator towards the poles and returning cold water back towards the tropics. This slow circulation takes centuries to complete a full cycle, yet it plays a central role in stabilizing Earth's climate. If these currents weaken or shift, the consequences ripple outward across continents. Above the oceans, the atmosphere responds. Warm water fuels storms. Hurricanes draw their strength from the heat stored in the sea. As warm, moist air rises, it feeds towering storm systems that can grow into vast spirals visible from space. When hurricanes pass over cooler waters or land, they weaken, starved of their energy source. But oceans do more than power storms. They influence wind patterns on a global scale. Trade winds, westerlies, and polar winds form as air moves from regions of high pressure to low pressure, guided by Earth's rotation. This movement bends winds into curved paths, shaping weather systems across the planet. These winds, in turn, push ocean currents, reinforcing the cycle. At times, this balance shifts. Every few years, the Pacific Ocean warms along the equator in an event known as El Niño. Though the temperature change may seem small, just a degree or two, the effects are immense. Winds weaken, rainfall patterns shift, floods strike some regions while drought grips others. South America may experience torrential rains, while Australia and parts of Asia dry out. Hurricanes may strengthen in some basins and weaken in others. Winters in North America can become milder or wetter, while other regions face unusual cold. El Niño is not a storm, but a planetary pulse, a reminder that the ocean and atmosphere move in rhythm. Its counterpart, La Niña, brings cooler ocean temperatures and often opposite effects. Winds strengthen, storm tracks shift again. Regions that were dry may flood, while others grow parched. Together, El Niño and La Niña form a natural oscillation, a swinging pendulum of heat and cold that reshapes global weather every few years. High above these processes, the atmosphere organizes itself into layers. The lowest layer, the troposphere, is where all weather occurs. It extends from the ground up to about 12 kilometers. Here, temperatures generally decrease with height, allowing warm air to rise and cold air to sink. This vertical movement drives clouds, storms, and winds. Above it lies the stratosphere, a calmer region where temperature increases with height due to the presence of ozone. This layer absorbs harmful ultraviolet radiation from the sun, protecting life below. Weather here is rare, but its influence is profound. Sometimes disruptions in the stratosphere can cascade downward, altering surface weather. One of the most dramatic examples is the polar vortex. High above the Arctic, a massive pool of cold air spins around the pole, contained by strong winds. Most of the time, it remains locked in place, but when those winds weaken, the vortex can wobble or split, allowing Arctic air to spill southward. When this happens, regions far from the poles experience sudden, extreme cold. Rivers freeze, cities grind to a halt. These events are not new, but they have become more visible in recent years, capturing headlines and reminding us that the Arctic is deeply connected to the rest of the world. The atmosphere is not isolated from space either. Above the stratosphere lies the mesosphere, where meteors burn up in streaks of light. Higher still, the thermosphere glows with auroras when charged particles from the sun collide with Earth's magnetic field. These auroras, the northern and southern lights, are a form of space weather. Solar winds stream outward from the sun, interacting with Earth's magnetic shield. When particles spiral toward the poles, they excite gases in the upper atmosphere, causing them to glow in greens, reds, and purples. Though beautiful, solar storms can disrupt satellites, communication systems, and power grids. They remind us that Earth's weather system extends beyond clouds and rain, reaching into the space environment that surrounds the planet. Back on Earth, ice plays a critical role. Glaciers and sea ice reflect sunlight back into space, helping regulate temperature. This reflectivity, known as albedo, acts like a planetary mirror. When ice melts, darker surfaces are exposed, absorbing more heat and accelerating warming. Glaciers themselves are not static. They move slowly, flowing like rivers of ice. Over centuries, they carve valleys, grind mountains, and transport enormous boulders across landscapes. During the last ice age, glaciers reshaped entire continents. Icebergs break away from glaciers and drift into the sea, hiding most of their mass beneath the surface. As they melt, they release fresh water, subtly altering ocean circulation. Beneath frozen ground lies permafrost, soil that has remained frozen for thousands of years. Within it are trapped ancient air bubbles, seeds, microbes, and even preserved animals. As permafrost thaws, it releases greenhouse gases like methane and carbon dioxide, further influencing climate. Weather leaves records of itself everywhere. Tree rings preserve histories of drought and rain. Ice cores trap ancient atmospheres. Sediments reveal floods and shifts in climate stretching back tens of thousands of years. These natural archives allow scientists to reconstruct Earth's past and understand how weather and climate have shaped life. Throughout history, weather has guided migration, agriculture, and survival. Rains determined where civilizations could flourish. Droughts forced populations to move. Floods renewed fertile plains while destroying settlements. Weather has quietly shaped human history as surely as wars and inventions. Even today, weather continues to influence the movement of life. Birds ride invisible rivers of warm air called thermals, gliding across continents without flapping their wings. Butterflies migrate thousands of miles, guided by sunlight, wind, and temperature. Whales follow shifting currents rich with food. Entire ecosystems move to the rhythm of the atmosphere. The air itself carries travelers. Dust from the Sahara crosses the Atlantic, fertilizing the Amazon rainforest. Smoke from wildfires seeds clouds thousands of miles away. Tiny particles influence how clouds form, how rain falls, and how sunlight is scattered. Human activity has become part of this system. Cities trap heat, creating urban heat islands. Skyscrapers bend winds at street level. Aircraft leave contrails that spread into thin clouds, subtly altering local temperatures. Pollution changes the color of sunsets, scattering light into deep reds and oranges. The atmosphere responds to everything placed within it. And yet, despite satellites, supercomputers, and decades of study, weather remains chaotic. Small changes can lead to large outcomes. A slight shift in temperature or pressure can redirect storms or alter rainfall patterns thousands of miles away. This sensitivity is known as the butterfly effect, the idea that even tiny disturbances can ripple outward into vast consequences. Weather can be modeled, predicted, and understood to a degree, but it can never be fully controlled. It remains a system of endless motion, forever balancing on the edge between order and chaos. As we descend once more towards the surface, one truth becomes clear. Weather is not a collection of isolated events. It is a single connected system, ocean, air, ice, land, and life, moving together in an intricate dance. Weather is often gentle, a breeze through trees, a passing cloud, light rain tapping against a window, but the same forces that bring comfort can also unleash destruction. When balance breaks, weather turns extreme. Extreme weather is not a separate system. It is weather pushed beyond familiar limits, amplified by heat, moisture, pressure, and motion. To understand why extremes occur, we must first understand energy. The sun delivers energy unevenly across the planet. The equator receives far more heat than the poles. This imbalance is what drives winds, currents, and storms. Normally, Earth redistributes this energy smoothly, but when heat builds up faster than it can be dispersed, tension grows within the system. That tension is released as extreme events. Heat waves are among the most silent yet deadly forms of extreme weather. Unlike storms, they arrive without thunder or spectacle. Days grow hotter. Nights offer little relief. The air becomes heavy and unmoving. A heat wave occurs when a region of high pressure becomes trapped over an area. This high-pressure dome pushes air downward, preventing clouds from forming. Sunlight pours in unchecked. Temperatures climb day after day. As the ground heats up, it releases warmth back into the air, reinforcing the heat. Cities suffer most. Concrete, asphalt, and buildings absorb heat during the day and release it slowly at night, keeping temperatures elevated around the clock. Human bodies rely on evaporation, sweat, to cool down. But when humidity is high, sweat evaporates more slowly. The body overheats. Heat exhaustion sets in. In severe cases, organs begin to fail. Heat waves kill more people globally each year than hurricanes, floods, and tornadoes combined. They strain power grids, damage crops, and trigger wildfires. Yet they often go unnoticed until the toll becomes undeniable. Wildfires are another expression of stored heat released violently. Fire requires three elements: heat, fuel, and oxygen. Prolonged heat waves dry out vegetation, turning forests and grasslands into tinder. A single spark, lightning, a downed power line, or human activity can ignite an inferno. Once burning, fires generate their own weather. Rising hot air creates powerful updrafts that draw in oxygen from surrounding areas, intensifying the flames. Smoke particles rise high into the atmosphere, sometimes forming fire-driven thunderstorms known as pyrocumulonimbus clouds. These firestorms can produce lightning, igniting new fires miles away. Ash travels across continents, sunlight dims, air quality deteriorates far beyond the burn zone. Fire reshapes landscapes, it clears old growth, releases nutrients into the soil, and opens space for new life. But when fires grow too frequent or intense, ecosystems struggle to recover. Floods represent the opposite extreme, too much water arriving too quickly. Flooding occurs when rainfall exceeds the land's ability to absorb it or when rivers overflow their banks. Urban areas are particularly vulnerable. Pavement prevents water from soaking into the ground, channeling it instead into streets and drains that quickly become overwhelmed. In mountainous regions, rain falling on steep slopes rushes downhill with tremendous force. Flash floods can develop in minutes, sweeping away vehicles, homes and lives before warnings can be issued. Coastal flooding adds another layer of complexity. Storm surges driven by hurricanes push seawater inland, raising water levels far above normal tides. Even a modest rise in sea level can dramatically increase flood damage during storms. Floodwaters carry more than water. They transport debris, chemicals, sewage, and pathogens. Long after waters recede, communities face contamination, displacement, and disease. Droughts, though slower to develop, are equally devastating. A drought is not simply a lack of rain, it is a prolonged imbalance between water supply and demand. Rainfall may decrease slightly, but rising temperatures increase evaporation, drying soils faster than they can be replenished. Crops fail, reservoirs shrink, rivers slow to a trickle, livestock suffers, food prices rise, entire regions become unstable. Historically, droughts have played a role in the collapse of civilizations. The fall of ancient societies often coincided with extended dry periods that undermined agriculture and forced mass migration. Even today, drought can fuel conflict. Competition for water intensifies. Rural populations move towards cities. Political systems strain under pressure. Storms are perhaps the most dramatic expressions of extreme weather. Thunderstorms form when warm, moist air rises rapidly into cooler layers above. As the air cools, water vapor condenses into towering clouds. Gravity pulls droplets downward as rain. Updrafts and downdrafts collide, producing lightning, hail, and gusty winds. In certain conditions, thunderstorms organize into more dangerous systems. Supercell storms contain rotating updrafts that can persist for hours. These storms produce large hail, intense lightning, and tornadoes, violently rotating columns of air that can tear buildings apart. Tornadoes form when wind speed and direction change with height, creating horizontal rotation that is tilted upright by rising air. The resulting vortex can reach wind speeds exceeding 300 miles per hour, though most are far weaker. Despite their power, tornadoes are narrow. Their paths of destruction may be only a few hundred meters wide, leaving neighboring areas untouched. This unpredictability makes them especially terrifying. Hurricanes, known as cyclones or typhoons in other regions, are the largest and most complex storms on Earth. They form over warm ocean waters when conditions align. High sea surface temperatures, low wind shear, and atmospheric instability. Warm air rises from the ocean surface, releasing heat as it condenses into clouds. This heat fuels further rising, creating a feedback loop. As the storm organizes, it begins to rotate due to Earth's spin. Bands of thunderstorms spiral inward toward a calm center, the eye, where air sinks and skies may briefly clear. Hurricanes draw energy from warm water. As long as they remain over the ocean, they can strengthen. Once they move over land or cooler waters, they weaken, deprived of their heat source. The damage from hurricanes comes not only from wind, but from storm surge, rainfall, and flooding. Inland areas far from the coast may experience catastrophic floods days after landfall. Extreme cold is another face of weather's power. Cold waves occur when polar air masses push southward, often following disruptions in the polar vortex. Temperatures plunge, infrastructure designed for milder climates fails, power grids collapse, pipes freeze, transportation halts. Cold air is dense and heavy. When it settles over a region, it can remain for days or weeks. Wind amplifies the danger through wind chill, increasing heat loss from exposed skin. Animals and plants adapted to specific climates suffer when cold extremes fall outside normal ranges. Agriculture is particularly vulnerable to unexpected freezes during growing seasons. Across all these extremes, one factor stands out: variability. Weather has always varied. Extremes are part of Earth's natural rhythm, but what concerns scientists is not simply the existence of extreme events, it is their changing frequency, intensity, and duration. As global temperatures rise, the atmosphere holds more moisture. Warm air can contain more water vapor. This amplifies rainfall when storms occur, increasing flood risk. At the same time, evaporation accelerates, intensifying drought between storms. Heat waves become longer and more intense. Fire seasons lengthen. Storms draw from warmer oceans, increasing their potential strength. This does not mean every extreme event is caused by climate change. Weather remains complex, but the background conditions have shifted, loading the dice toward more intense outcomes. Extreme weather tests societies. Early warning systems save lives, but they require trust, infrastructure, and communication. Emergency. Responses depend on planning and resources. Recovery depends on resilience and cooperation. Communities with fewer resources suffer most. Informal housing collapses under storms. Poor air quality affects those without access to healthcare. Drought devastates subsistence farmers. Yet humans are not passive victims. We adapt. We build levees and dams. We redesign cities to absorb water and reflect heat. We develop drought-resistant crops. We improve forecasting models that peer days and weeks into the future. Modern weather prediction relies on satellites, radar, ocean buoys, and supercomputers. These tools ingest massive amounts of data, solving complex equations that describe atmospheric motion. Forecasts are more accurate today than ever before. A 5-day forecast now is as reliable as a 2-day forecast was decades ago. Warnings allow evacuations, preparations, and life-saving decisions. Still, uncertainty remains. Weather systems interact across scales, from microscopic particles to planetary waves. No model can capture every detail. Prediction is a balance between knowledge and chaos, and so weather remains both familiar and mysterious. It shapes landscapes, challenges societies, and reminds us of forces larger than ourselves. Long before satellites orbited the Earth, before computers calculated pressure gradients and wind vectors, humans looked to the sky for survival. Weather was not curiosity, it was fate. A failed monsoon meant famine, a late frost meant hunger, a violent storm meant death. Entire civilizations learned, often painfully, that understanding the sky was not optional, it was essential. The earliest humans became the first meteorologists without realizing it. They watched clouds, winds, animal behavior, and the movement of stars. Patterns were memorized, passed down orally, and embedded in culture. Farmers noticed that certain cloud shapes preceded rain. Sailors learned that changing winds meant danger. Shepherds observed how animals reacted before storms. These observations were not superstition. They were early science, built on repetition and survival. Ancient civilizations formalized this knowledge. In Mesopotamia, clay tablets recorded weather events alongside crop yields. In Egypt, the flooding of the Nile was tracked carefully. tied to seasonal rains far upstream. In China, detailed records of floods, droughts, and unusual weather stretch back thousands of years, forming one of the longest continuous climate archives in human history. The Greeks attempted to explain weather philosophically. Aristotle wrote Meteorologica, describing clouds, winds, rain, and celestial phenomena. Though many explanations were incorrect, the attempt to understand weather as a natural process rather than divine punishment marked a turning point. In the Islamic Golden Age, scholars expanded on Greek ideas, emphasizing observation and classification. Winds were named and mapped, rainfall patterns were recorded. The relationship between geography and climate was explored with surprising accuracy. Still, prediction remained limited. Weather forecasts were local, short-term, and uncertain. A darkening horizon, a sudden shift in wind, or the smell of rain in the air offered clues, but storms still arrived unannounced. The modern era of weather forecasting began with one simple realization: weather is connected across distance. In the 19th century, the invention of the telegraph transformed meteorology. For the first time, weather observations from different locations could be shared rapidly. A storm reported in one city could be tracked as it moved toward another. This changed everything. Meteorologists began mapping pressure systems. They discovered that storms were not isolated events, but organized systems traveling along predictable paths. Low-pressure areas brought clouds and rain. High-pressure systems brought clear skies. Weather maps were born. By plotting temperature, pressure, wind, and precipitation, forecasters could visualize the atmosphere in motion. Patterns emerged. Storm tracks became visible. Prediction shifted from intuition to analysis. The next breakthrough came from physics. In the early 20th century, scientists realized that weather obeys mathematical laws. The atmosphere behaves like a fluid, governed by equations describing motion, energy, and mass. In theory, if all variables were known, weather could be predicted precisely. In practice, this was impossible. The number of variables was enormous. Calculations were complex. Early attempts at numerical forecasting took longer than the weather itself to evolve. Then came computers. After World War II, early computers were applied to weather prediction. Though primitive by today's standards, they could perform calculations far faster than humans. Numerical weather prediction became possible. Forecast accuracy improved steadily. Satellites revolutionized meteorology once again. From space, Earth could be observed as a whole. Clouds, storms, and atmospheric circulation became visible in real time. Satellites measured temperature, humidity, wind speed, sea surface temperature, and even atmospheric composition. Weather was no longer inferred, it was observed directly. Radar systems complemented satellites, allowing meteorologists to see inside storms. Rain intensity, hail, wind shear, and rotation could be detected, improving warnings for severe weather. Together, these technologies created a global observing system. Every day, millions of observations are collected from weather stations, aircraft, ships, ocean buoys, balloons, and satellites. This data feeds into powerful supercomputers that simulate the atmosphere forward in time. Forecasts are now probabilistic rather than absolute. Instead of a single predicted outcome, models generate multiple scenarios. Forecasters assess confidence, uncertainty, and risk. This approach acknowledges a fundamental truth: weather is chaotic. Small uncertainties in initial conditions grow over time. A slight error in temperature or wind measurement can alter a forecast days later. This limits predictability. Short-term forecasts, hours to days, are highly accurate. Medium-range forecasts, up to a week, are reliable. Beyond that, certainty fades. Seasonal forecasts focus on trends rather than specific events. Despite these limits, forecasting saves lives. Early warnings allow evacuations ahead of hurricanes. Flood forecasts prompt dam releases and road closures. Heat alerts protect vulnerable populations. Aviation relies on precise forecasts to ensure safety. Yet forecasting is not just about science, it is about communication. A perfect forecast that is not understood or trusted is useless. Meteorologists must translate complex data into clear messages. Authorities must act on warnings. Communities must respond. Failures often occur not because forecasts were wrong, but because warnings were ignored, misunderstood, or delayed. Cultural, political, and social factors shape how societies respond to weather threats. Some communities trust institutions, others do not. Some have resources to evacuate, others are trapped by poverty or geography. Weather forecasting reveals inequalities. Those with access to information, infrastructure, and mobility are safer. Those without face greater risk. As climate patterns shift, forecasting becomes more challenging. Historical data, the foundation of many models, may no longer represent future conditions. Extremes fall outside past experience. Rare events become less rare. Meteorologists adapt by refining models, incorporating new data, and developing better ways to quantify uncertainty. Artificial intelligence is now entering the field. Machine learning algorithms analyze vast data sets, identifying patterns humans might miss. AI models can complement traditional physics-based models, improving short-term predictions and extreme weather detection. Still, technology alone is not enough. Understanding weather also requires humility. Despite all advances, the atmosphere retains an element of unpredictability. This uncertainty is not failure, it is a natural feature of complex systems. Weather forecasting teaches us something deeper about our relationship with nature. We can observe, model, and anticipate, but not control. We are participants in the system we study. Human activity influences weather patterns. Urbanization alters local climates. Emissions affect atmospheric composition. Land use changes influence rainfall and temperature. In trying to predict weather, we also confront our role in shaping it. This realization shifts the narrative. Weather is no longer something that simply happens to us. It is something we interact with, sometimes unknowingly, sometimes irresponsibly. Understanding weather becomes a responsibility. Responsibility to prepare, responsibility to communicate clearly, responsibility to reduce vulnerability, and responsibility to ask difficult questions about how we live within Earth's systems. As forecasting grows more precise, society faces a paradox. We know more than ever, yet the stakes are higher than ever. The challenge is no longer whether we can predict weather. The challenge is whether we will act on what we know. As we move towards the final part of this journey, one question remains. What does the future of weather look like in a changing world? And how will humanity adapt to forces that have always shaped our destiny? If this story has helped you see weather not just as daily forecasts, but as a living system tied to history, science, and society, then you already understand why these conversations matter. For most of human history, weather was treated as background noise, powerful, mysterious, but largely unchangeable. Storms came and went, seasons shifted, extremes were endured, remembered, and folded into folklore. Today, that perception has changed. The sky is still vast, the winds still move as they always have, but something fundamental is different. The patterns that once repeated with quiet reliability are becoming harder to recognize. Records are broken more frequently, extremes linger longer, familiar climates behave in unfamiliar ways. This is not a sudden transformation. It is the result of slow, cumulative changes layered over generations. At the center of this shift lies energy. Earth's climate system is governed by balance between incoming solar radiation and outgoing heat. For thousands of years, this balance fluctuated within a relatively narrow range. Ice ages came and went, Warm periods followed, life adapted, but in the past 2 centuries, the balance has been altered at a speed unmatched in geological history. The burning of fossil fuels, deforestation, and industrial activity have increased concentrations of greenhouse gases in the atmosphere. These gases trap heat, reducing the amount that escapes back into space. The result is a gradual warming of the planet. This warming does not distribute itself evenly. Land heats faster than oceans. Polar regions warm faster than the tropics. Nights warm faster than days. Winters warm faster than summers. These uneven changes disrupt the delicate gradients that drive weather. Jet streams, fast-moving rivers of air high in the atmosphere, depend on temperature differences between the equator and the poles. As the Arctic warms more rapidly, this temperature contrast weakens. The jet stream slows and becomes more wavy. When the jet stream stalls, weather patterns linger, heat waves persist, storm systems park over regions, delivering prolonged rainfall. Cold air intrusions become sharper and more erratic. Weather that once moved on now gets stuck. The oceans absorb much of the excess heat, acting as buffers. But this comes at a cost. Warmer oceans expand, contributing to sea level rise. They also store energy that can be released during storms. Tropical cyclones draw strength from warm water. While not every storm becomes stronger, the most intense storms are becoming more destructive, carrying heavier rainfall and producing higher storm surges. Rising seas amplify these impacts. A storm surge that once flooded a coastal road now inundates neighborhoods. High tides reach further inland. Communities that existed at the edge of the sea for generations face difficult choices. Some build barriers, some elevate structures, some retreat. Sea level rise is slow but relentless. It does not announce itself with drama. It accumulates centimeter by centimeter, reshaping coastlines quietly until thresholds are crossed. Inland, changes are equally profound. Snowpack in mountain regions acts as a natural reservoir, storing winter precipitation and releasing it gradually in spring and summer. As temperatures rise, more precipitation falls as rain instead of snow. Snow melts earlier, rivers peak sooner. Water arrives when it is least needed and disappears when demand is highest. Agriculture, built around predictable seasons, struggles to adjust. Farmers face planting seasons disrupted by late frosts or early heat. Pests expand into new regions. Pollination cycles shift. Droughts intensify not only because rainfall decreases, but because evaporation accelerates. Soils dry faster, vegetation becomes stressed, fire risk increases. Wildfires, once limited to specific seasons, now burn longer and more intensely. Smoke blankets cities far from the flames. Air quality declines, affecting millions. Weather extremes intersect with human systems in complex ways. Power grids strain under heat waves as demand for cooling rises. Hydropower declines during drought. Transportation networks buckle under floods. Supply chains are disrupted. Insurance models struggle to keep pace with changing risk. Some areas become uninsurable. Reconstruction costs soar. Inequality deepens as vulnerable communities lack resources to recover. Weather becomes not just a physical challenge, but an economic and social one. Adaptation is not uniform. Some regions invest in resilience, flood defenses, heat-resistant infrastructure, early warning systems. Others lack funding or political stability. Global disparities widen. Yet adaptation is not merely technological, it is cultural. Communities must learn to live with uncertainty, to accept that historical norms may no longer apply, to prepare for a wider range of possibilities. This requires trust in science, institutions, and collective action. But trust is fragile. Misinformation spreads easily. Weather events are politicized. Scientific warnings are sometimes dismissed as exaggeration or alarmism. Yet the evidence accumulates. Temperature records fall year after year, glaciers retreat, sea ice declines. Phenomena once considered rare occur more frequently. Scientists analyze trends carefully. They separate signal from noise. Individual events cannot be attributed to climate change alone, but patterns reveal a clear influence. This distinction is often misunderstood. Climate change does not create storms from nothing. It alters the environment in which storms form. It changes probabilities. It increases the likelihood of extremes. Weather remains variable. Cold days still occur. Snow still falls. But the baseline has shifted. Understanding this nuance is crucial. Oversimplification undermines credibility. Denial ignores risk. Between these extremes lies informed awareness that empowers preparation rather than fear. Weather forecasting evolves in response. Models now incorporate climate projections, allowing planners to anticipate future conditions rather than relying solely on past data. Cities design infrastructure for rainfall totals not yet experienced. Coastal planners consider sea levels decades ahead. Early warning systems integrate social science, ensuring alerts reach those most at risk in language they understand. Community-based approaches emphasize local knowledge alongside scientific expertise. Indigenous communities, in particular, hold generations of environmental observation. Their insights into seasonal shifts, animal behavior, and ecosystem health complement modern data. Resilience emerges from blending old knowledge with new tools. There is no single solution. Mitigation, reducing emissions, addresses long-term drivers. Adaptation addresses immediate impacts. Both are necessary. The atmosphere responds slowly. Even if emissions stopped today, existing greenhouse gases would continue influencing climate for decades. Weather changes already set in motion will continue. This reality underscores urgency without despair. The future is not fixed. The range of possible outcomes depends on choices made now. Weather will always test humanity, but the severity of those tests is not entirely beyond influence. Understanding weather deeply, honestly, is the first step. Not as distant science, not as abstract debate, but as lived experience. Every forecast, every warning, every adaptation effort reflects an attempt to coexist with forces larger than ourselves. As we approach the final chapter of this story, the question is no longer whether weather is changing. The question is how we will respond, not just as individuals, but as societies sharing one atmosphere, one ocean, one sky. At the end of every storm, the sky clears, clouds break apart, winds settle, rain-soaked ground begins to dry. Life resumes its familiar rhythms. This cycle, disruption followed by calm, has played out since the Earth first formed an atmosphere. Weather is not an enemy. It is not a punishment. It is not a force with intention. It is a process, a living, moving expression of energy, shaped by physics, guided by balance, and influenced by everything it touches, including us. Throughout this journey, we have followed weather from its origins in sunlight and motion, through oceans and winds into extremes that test survival, and finally into an era where human activity has become part of the system itself. What emerges is not a story of doom, nor a story of control, but a story of relationship. Humans and weather are bound together. We breathe the atmosphere that circulates heat across the planet. We drink water lifted by evaporation and returned by rain. Our food grows in soils shaped by climate and nourished by seasonal cycles. Every civilization has been built under a specific sky. Ancient cities rose along rivers fed by predictable floods. Trade routes followed prevailing winds. Architecture reflected local climates, thick stone walls for heat, sloped roofs for snow, open courtyards for airflow. Weather quietly shaped culture, language, and belief. Even today, weather defines daily life. It dictates what we wear, how we travel, when we work, and where we live. It influences mood, memory, and imagination. Despite modern technology, we still glance at the sky before stepping outside. Yet something has shifted in the modern relationship. For centuries, weather was accepted as uncontrollable. Preparation meant adaptation, storing grain, building shelter, migrating when necessary. In the industrial age, humanity gained unprecedented power. We learned to extract energy buried for millions of years. We reshaped landscapes, redirected rivers, and filled the atmosphere with byproducts of progress. At first, the sky seemed vast enough to absorb anything. It is only recently that we have begun to understand that the atmosphere, while immense, is not infinite. Weather responds to cumulative change, not immediately, not dramatically at first, but persistently. This delayed response is part of the challenge. Human systems operate on short timelines: elections, fiscal quarters, lifetimes. Weather and climate operate on longer scales, blending immediate variability with long-term trends. This mismatch creates tension. A single cold winter does not negate warming trends. A single storm does not define a climate shift. Understanding emerges not from isolated events, but from patterns observed over time. This requires patience and trust in evidence. Trust, however, is fragile. Weather has become a symbol in broader cultural debates. Extreme events are sometimes weaponized in arguments, oversimplified, or dismissed entirely. In this noise, nuance is often lost, yet weather does not argue. It responds. Rain falls according to physics. Heat accumulates according to energy balance. Winds shift according to pressure gradients. Nature does not take sides. The responsibility lies with interpretation and action. One of the most profound lessons weather teaches is humility. Despite satellites orbiting the Earth and computers performing trillions of calculations per second, uncertainty remains. Forecasts improve, but never reach absolute certainty. Chaos limits predictability. This is not a failure of science, it is a feature of complex systems. Acknowledging uncertainty does not weaken understanding, it strengthens it. Weather reminds us that knowledge is not control, it is guidance. Guidance to prepare rather than dominate. Guidance to adapt rather than resist blindly. Across the world, communities are already responding. Some redesign cities to absorb water rather than repel it. Green roofs, permeable streets, restored wetlands. Others reintroduce shade and vegetation to cool urban heat islands. Farmers adjust planting schedules and crop varieties. Architects rethink building orientation and materials. Emergency planners refine warning systems to reach those most at risk. These efforts are not signs of defeat, they are signs of learning. History shows that societies capable of adaptation endure. Those that ignore environmental signals struggle. This has always been true, long before modern climate science. What is different now is scale. Weather connects every region. Emissions released in one place influence conditions elsewhere. Storms formed over distant oceans affect inland communities thousands of miles away. Borders do not stop the wind. This interconnectedness demands a broader perspective. Responsibility becomes shared, not shared equally because capacity and contribution differ, but shared in consequence. Weather does not distinguish between ideologies. It does not wait for consensus. It responds to physical reality. Understanding this does not require fear. It requires clarity. Clarity that allows societies to weigh risks honestly. Clarity that separates scientific evidence from political narrative. Clarity that prioritizes resilience over denial. Weather also teaches perspective. Compared to geological time, human history is brief. Compared to the atmosphere's depth, our cities are thin layers at the surface. Compared to the sun's energy, our technologies are modest. Yet within this scale, human choices matter. Small changes multiplied across billions of people and decades reshape systems. This mirrors weather itself, where small disturbances can ripple into large effects. The same principle applies in reverse. Incremental improvements accumulate. Preparedness reduces harm. Cooperation amplifies impact. The future of weather is not a single outcome, it is a range of possibilities. Some paths lead to greater instability, where extremes strain systems beyond capacity. Other paths lead to managed change, where societies anticipate risks and reduce vulnerability. Which path dominates depends less on the sky and more on what happens beneath it. Education plays a central role. Understanding weather as a system, not just daily forecasts, empowers individuals to interpret events accurately. It reduces fear driven by misunderstanding. It builds appreciation for the complexity of the planet we inhabit. This understanding fosters responsibility rather than paralysis. Responsibility to demand informed decisions. Responsibility to prepare communities. Responsibility to pass knowledge forward. Weather literacy is not specialized knowledge, it is survival knowledge. From recognizing heat stress symptoms to understanding flood warnings, weather awareness saves lives. As technology advances, access to information expands, but information alone is not enough. Context matters, stories matter. The way we frame weather as random chaos, divine punishment, or political weapon shapes response. Framing it as a system we participate in encourages agency. Agency does not mean control. It means engagement. Engagement with science, engagement with community, engagement with long-term thinking. This documentary has traced weather from physical foundations to human consequences, not to provoke fear, but to restore perspective. The sky above us is not separate from life below. It is an extension of it. Every breath, every drop of rain, every gust of wind is part of a shared system that sustains life on Earth. We are not observers standing outside this system. We are inside it. And that realization carries weight. It means our actions ripple outward, just as weather does. It means resilience is built collectively. And it means the future is not written solely by clouds and currents, but by choices made under them. As you step outside next time, whether under clear skies or gathering clouds, consider the invisible processes at work above and around you. Consider the balance being negotiated every moment between heat and motion, water and air, and consider how understanding that balance changes the way we live beneath it. Because the story of weather is not just the story of storms, it is the story of humanity learning, again and again, how to live under one sky. If this journey has changed the way you see the atmosphere above you, if it has encouraged reflection rather than reaction, then its purpose has been served. The conversation does not end here. It continues wherever people choose to understand rather than dismiss, to prepare rather than ignore, and to share knowledge rather than keep it silent. Under the same sky, that choice belongs to all of us.